When an object is raised, it has gravitational potential energy. And using a simple lever setup like this, its energy can be transferred to a smaller object. Now when I drop this weight, it will accelerate towards the ground, converting its gravitational potential energy into kinetic energy. As it impacts the plank of wood, its momentum will be transferred to the smaller object, launching it higher into the air. But the problem is with this setup is that it's really inefficient and the tennis ball doesn't go that high. This is where this trebuchet comes in. I built this about a year ago and it's designed and optimised to transfer the gravitational potential energy of this counterweight into kinetic energy of this projectile, a tennis ball, as efficiently as possible. When released, this tennis ball goes from 0 to 130 miles an hour in under a second and launches about 80 metres downrange. So how about we make a few adjustments to see how high we can launch a projectile straight up into the air. To measure how high the projectile is launched from the trebuchet, I'm going to be using an altimeter. However, I don't just want to stick this altimeter inside of the tennis ball for a number of different reasons. The first reason being that this tennis ball will most likely go quite high into the air, and that also means that it will come down quite quickly and hit the ground quite hard, which could risk breaking the altimeter. Also, tennis balls aren't that aerodynamic with their furry covered surface. So what I want to do is 3D print a rocket shaped projectile which will be more aerodynamic than the tennis ball and also have a parachute deployment system so that the altimeter can float down nice and safely. So here is the first prototype. As you can see, it's not very aerodynamic at the top, and that's because I haven't actually built the parachute deployment mechanism into this yet. This is sort of like a dummy model, and I've put a foam nose cone on it so that when it comes back down, hopefully it won't destroy itself or anything else around it on the ground. The reason why I've built this model is to test the launch portion of the flight. So I've got the 3D printed projectile mounted inside of the trebuchet, and I've got the string wrapped up around the release pin. So yeah, fingers crossed this goes successfully, and I think we should probably step back a little bit and give it a quick test launch. Okay, in 3, 2, 1. Well, that was a successful release. Didn't go as high as I'd hoped. Right, let's try this again. In 3, 2, 1. Oh, that's not good. Right, so that previous launch had the exact same setup in terms of pin release and the sling mounting. However, instead of going forwards, it went backwards and ended up in my next door neighbour's garden. I think we need to do some serious rethinking about the design of this. Over the next few days, I decided to try it a few more times with a few different attachment methods, but still struggled to get it to launch reliably. Even when the trebuchet threw it in the correct direction, keeping the projectile pointing directly into the oncoming air was very difficult. This causes a lot of drag and therefore defeats the whole point of its purpose. In fact, the release velocity was barely above 30 meters per second, whereas the tennis ball releases at around 50 meters per second, and its rotation doesn't have much of an effect. So it's time for plan B. So plan B is to scrap this rocket-shaped projectile and move back to a sphere-shaped projectile like the tennis ball. However, what's more aerodynamic than a tennis ball? A golf ball. Golf balls are famous for their dimple-shaped aerodynamic properties. However, it's going to be very difficult to fit this altimeter and also its battery inside of a golf ball, as well as a parachute deployment system. So what I've done is I've 3D printed an enlarged golf ball. This is roughly 187% scale, so it's almost double the diameter of a regular golf ball, and I should easily be able to fit all of the electronics and a parachute system inside. Now this current ball doesn't have anything special to it, it's just like a dummy model, so I can give it a few test launches to get an idea of release velocity and also flight trajectory. And also I've made a larger sling for it because the old sling
wouldn't fit this ball. It was designed for tennis ball size. So let's load this onto the trebuchet and see how high this thing will go.
Right, first test of the oversized 3D printed golf ball in 3, 2, 1. Wow, that's high. That went so high. Right, let's try that again. In 3, 2, 1. Wow. That's never going to get old.
So this new ball works incredibly well and it goes so high into the air. I'm really pleased with the way it performs, and more importantly, it releases reliably from the sling. Now, in terms of release velocity, this is slightly slower than the tennis ball, but that's expected because it does weigh a bit more. I believe the tennis ball is about 2/3 the weight or mass of this ball. But the real question is, how high does this ball actually go? Now, this is the ball that will give us the answer, or at least the various parts of the ball. Now, in terms of electronics, there's obviously the altimeter, there's also the battery which powers everything, and then there is the electronics to control the parachute deployment. With many of my projects, I make them radio controlled so that I can flick a switch on a radio control transmitter and it will deploy the parachute. But I wanted to make this fully automated. So inside of here, there is an accelerometer which will basically detect when the ball is launched from the trebuchet. When it detects over 2 Gs of acceleration, the Arduino will start a 4-second timer. After 4 seconds is up, this servo will move, pulling this pin and also deploying the parachute. So let's assemble this ball quickly and see whether the parachute can be deployed. So this rubber band holds the 2 halves of the ball together and hooks around the servo pin. And if I give this a quick shake, in 4 seconds time, it should split open like an oddly coloured Pokeball. So give it a shake. And then, there we go. And that deploys the parachute. So I think this is all ready for an actual test launch.
So I've got the parachute ball mounted inside of the trebuchet now. I haven't got the altimeter inside of it just yet because I want to test if it actually deploys the parachute successfully. I've also moved the trebuchet so that hopefully it will fire somewhat into the field and the parachute won't land in any of these trees either side. So let's see if this thing will actually work. Parachute projectile first test in 3, 2, 1. Come on, come on, come on, come on. First try. Nice. Yes! That is so cool. Test number 2 in 3, 2, 1. That is so satisfying. Floats down very slowly. Maybe I need a smaller parachute. Don't want it to drift too far in the wind.
I then carried out a few more test launches to make sure the parachute deployment was reliable, as well as capturing some more high-speed shots. Until one of the launches resulted in a catastrophic failure of the trebuchet arm, as well as the parachute getting stuck in a tree. So, whilst I source a new arm and figure out how to retrieve the parachute, let's take a more detailed look at what's going on. When the trebuchet is loaded, the counterweight of 15 kilograms is raised 1.22 meters from its end position. We can calculate its gravitational potential energy by multiplying the mass by the acceleration due to gravity and the height it's raised, giving a total stored energy of 179.5 joules. But let's round it to 180 joules because the bar that holds the weights to the arm probably adds a bit more mass. From this, we can calculate the maximum altitude the ball could theoretically reach by equaling it to the end gravitational potential energy of the ball. If we rearrange this equation for the height of the ball, we get a max theoretical altitude of 166.8 meters, or 550 feet. Now this altitude assumes the whole system is 100% efficient, and there is no drag acting on the ball, which obviously isn't realistic. But we can use this max value to work out the efficiency of the system once we know the final altitude. Oh, and here's my genius method of retrieving the parachute. Or maybe not. Let's skip to the actual launch.
Right, so I've now got the altimeter mounted inside of the ball, and I've also got a smaller parachute on it so it hopefully won't drift too far in the wind. It's quite windy right now, slight headwind, but hopefully it doesn't drift too far with a smaller parachute. So let's see how high this thing really goes. Okay, altimeter ball test in 3, 2, 1. Oh, that was a late deploy. Couldn't get much closer to the Trebuchet though. Let's check the altitude. Probably can't see that on camera, but it says 61 meters, which is almost exactly 200 feet. Let's do a few more launches and get an average max altitude.
So after gathering all the altitude data, the ball reached an average altitude of 59 meters, or 193.6 feet, which is about 35% of the estimated max altitude. This means that 65% of the total starting potential energy was lost. Now we can measure the release velocity of the ball using the high-speed footage, which gives us a speed of 41 meters per second. From this, we can calculate the kinetic energy of the ball just after release, and this shows that 49% of the energy is lost just in the launch itself, and the remaining 16% is lost due to drag. So this shows that the enlarged golf ball is either very aerodynamic or my Trebuchet is very inefficient. Either way, it's very satisfying to see this thing launch.
Altimeter ball test in 3, 2, 1. Oh yes. 1. Oh yeah. 1. Nice. Looks like the lid's come off. 1. Perfect.
Speaking of the Trebuchet design, I never got around to uploading the files to the internet, as Fusion 360 kept crashing every time I tried to export the model. So I've rebuilt the CAD model completely from scratch, and uploaded it so that you guys can build your own if you want to. The link to the files will be down in the description below. So there we have it, I've made the world's most safest Trebuchet projectile. If you enjoyed this video, or found it interesting, it'd be great if you could leave a thumbs up. If you're new to my channel and want to see projects similar to this, then click subscribe down below. And a huge thanks to all of my supporters over on Patreon. You guys make these videos possible, and I honestly couldn't do various projects like this without your support. So thank you very much. Thanks once again for watching, and I'll see you in the next video. Goodbye.
Oh no, deploy! Uh-oh, that's gone backwards. I don't think that was good. Don't know how well you can see that, but the ball looks like it's in multiple pieces. Not good.